Today we will see the article Riemann integral from real analysis, paper number M80601. This Riemann integral is related to the boundedness, continuity and differentiability of a function. This article we will see in two parts. In first part we will see the definition, upper sum and lower sum of the function, and in second part the definition of Riemann integral and corresponding theorem. So in first part we will see the definitions. First definition, maximum and minimum of the function. Let I be any bounded interval and f is a bounded function on the interval I. We define maximum of the function and minimum of the function as this: maximum for f over the interval I is equal to least upper bound of f of x belongs to interval I. Minimum for f over the interval I is defined as the greatest lower bound of the function f of x belongs to I, and omega for the function f corresponding to the interval I is the difference of maximum and minimum of the function in the corresponding interval. The second definition is here of subdivision. The finite subset x0, x1, x2, xn is said to be subdivision of the bounded interval AB if it satisfies this condition, that is a equal to x0 is strictly less than x1 is strictly less than x2 dash is strictly less than xn is equal to b. If there are two subdivisions sigma and tau, then tau is said to be a refinement of sigma if sigma is subset of tau, or this tau is obtained from subdivision sigma by adding at least one point in the subdivision sigma. Now if this sigma is subdivision is like this, the set x0, x1, x2 dash xn, then we define the corresponding component intervals like this. That is, the first component interval I1 is closed interval x0, x1. Second component interval I2 is equal to closed interval x1, x2. Third component interval I3 is x2, x3, and so on. The nth component interval In is the closed interval xn minus 1 xn. All these are called as a component intervals of the subdivision sigma. Next definition is of upper sum for the function. Here f is a bounded function over the closed bounded interval AB, and sigma is any subdivision of the closed bounded interval AB. Then we define upper sum for f corresponding to the subdivision sigma as here this upper sum for f corresponding to sigma is equal to summation k is equal to 1 to n. Maximum for f on the interval ik into mod of ik. Mod of ik means the length of that interval ik. Here I1, I2, In are the component intervals of the subdivision sigma. Similarly, we can define a lower sum also. The function is again bounded over the closed bounded interval AB. Sigma is any subdivision. Then lower sum for f corresponding to the subdivision sigma is defined as summation k is equal to 1 to n minimum of function f over the interval ik into length of interval ik, where this ik is the component intervals of the subdivision sigma. Obviously, we have the upper sum for function f is greater than or equal to lower sum for function f corresponding to the subdivision sigma. This equality holds in case of function is constant, otherwise it is unequal. Now we will see one theorem corresponding to this one. The statement of theorem is: let f be a bounded function on closed bounded interval AB, then every upper sum for f is greater than or equal to lower sum for f. That is, in the notation form, the same statement can be written as: if sigma and tau are any two subdivisions of closed interval AB, then upper sum for f corresponding to sigma is greater than or equal to lower sum for f corresponding to subdivision 2. We will prove this theorem like this. Here first we will consider the sigma star as a refinement of sigma. Then we will prove that upper sum for f corresponding to subdivision sigma is greater than equal to upper sum for f corresponding to refinement sigma star. Now this refinement sigma star we will consider by adding a single point in a subdivision sigma. So the corresponding component intervals will changes. Now the component intervals for subdivision sigma are I1, I2, dash Ik, dash In. Then the component intervals for the refinement sigma star will be like this: I1, I2, dash Ik star, Ik double star, dash In. And this Ik star interval is split up into two intervals. Now here they are like this: Ik is equal to Ik star union Ik double star, and length of interval Ik is equal to length of interval Ik star plus length of interval Ik double star. Since Ik star is subset of subinterval of Ik, clearly the maximum on this Ik star is less than equal to maximum of the function in Ik, and maximum of the function f in interval Ik double star is clearly less than maximum of the function in interval Ik. Now here we will calculate the upper sum for f corresponding to refinement sigma star. By definition it is summation j is equal to 1 to n, j is not equal to k, maximum of the function f over the interval ij into length of interval ij. And here maximum of function f over the interval Ik star.
Start.
Here upper sum for f corresponding to refinement sigma star is defined as here summation j is equal to 1 to n, I is not equal to k, j is not equal to k, maximum for function f over the interval ij into length of that interval, plus maximum of function f over interval Ik star into length of Ik star, and maximum of the function f over Ik double star into length of Ik double star. This is less than equal to summation j is equal to 1 to n, j is not equal to k. This part is as it is. Here we are changing that, we are replacing this maximum for f over interval Ik and maximum of f over Ik star, and that is replaced by maximum of f over Ik star, and therefore here we are writing here less than equal to, and here the length of this interval we are adding, and then this becomes the upper sum for f corresponding to sigma. So we have started from upper sum for f corresponding to sigma star, and we have obtained that this is less than equal to upper sum for function f corresponding to subdivision sigma. And so this proves our statement 1 that we have taken here is proved. Similarly, for lower sum we will have a tau star as a refinement of tau, and then we can prove by the similar way that lower sum for f corresponding to subdivision tau is less than equal to lower sum for function f corresponding to tau star. But here sigma union tau is a refinement of both sigma and tau. So from above statements 1 and 2 we get that the upper sum for f, here upper sum for f corresponding to subdivision sigma is greater than equal to upper sum for subdivision sigma union tau. It is greater than equal to lower sum for the function f corresponding to the subdivision sigma union tau, and it is greater than equal to lower sum for function f corresponding to subdivision tau. That is, clearly this upper sum for this subdivision sigma is greater than equal to lower sum for of the function corresponding to this subdivision tau, and hence we have proved that the any upper sum for function f over the interval is greater than lower sum for the function in the same interval. Now we will see the example corresponding to this one. Here we have taken a function f, and then we have taken the upper sum for f over the interval is greater than equal to upper sum for f corresponding to subdivision sigma is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for the function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is greater than equal to lower sum for function f over the interval is Here we define the function f of x as f of x is equal to x, where 0 is less than equal to x is less than equal to 1. Let sigma be the subdivision, this set 0, 1 by 3, 2 by 3, 1 of the closed bounded interval 0, 1. Then we have to compute upper sum and lower sum for the function f corresponding to this subdivision. Now, this subdivision is clearly, because here 0 equal to 0 is less than 1 by 3, is less than 2 by 3, is less than 1 equal to 1. Now, the corresponding component intervals to this subdivision are here I1 closed interval 0, 1, 3, I2 is the closed interval 1, 3, 2, 3, component interval third is the closed interval 2 by 3, 1. We can see clearly the length of all these component intervals is same, and that is, it is 1 by 3. Now we will have the maximum over these component intervals. Maximum for f over first component interval is 1 by 3. Maximum for function f corresponding to the second component interval is 2 by 3, and maximum for function f corresponding to the third component interval is 1. Similarly here minimum for function f in the first component interval is 0, in the second component interval is 1 by 3, and in the third component interval is 2 by 3. Now we calculate the upper sum for f corresponding to subdivision sigma. By definition it is summation k is equal to 1 to 3 maximum for function f over the interval ik into length of interval ik. And as per these values we will put here maximum of the function in first component interval is 1 by 3 into its length 1 by 3. Maximum of the function is 2 by 3 in the second component interval and into its length 1 by 3. And maximum of the function in third component interval is 1 into its length 1 by 3. Simplify this, we are getting it is equal to 2 by 3, and hence the upper sum for function f corresponding to the given subdivision is 2 by 3. Now similarly we will calculate the lower sum for function f corresponding to the given subdivision. It is defined like this here. It is the summation k is equal to 1 to 3 minimum of the function f over the interval ik into length of interval ik. As already we have defined here that minimum of the function over first component interval is 0 into its length 1 by 3. Minimum of the function in the second component interval is 1 by 3 into its length 1 by 3. And minimum of the function in the third component interval is 2 by 3 into its length 1 by 3. So simplify this, we are getting this is equal to 1 by 3, and hence the lower sum for the function f corresponding to the given subdivision sigma is 1 by 3. Hence we have calculated the upper sum and lower sum for the function for the given subdivision. We will see the second example here. The function here we will define as a f of x is equal to x again, and here x is such that 0 is less than equal to x is less than equal to 1. For each n belongs to I, we define a subdivision sigma n like this. It is the finite subset 0, 1 by n, 2 by n by n over the closed interval 0, 1. Here we have to compute limit n tends to infinity upper sum for function f corresponding to the subdivision sigma. Now we will solve this. We have given this subdivision sigma n. So we will check here. 0 is equal to 0 is less than 1 by n is less than 2 by n and is less than n by n is equal to 1. So it is the subdivision for on the closed bounded interval 0, 1. And the component intervals are here n, I1, I2 dash in are like this. The first component interval I1 is equal to closed interval 0, 1 by n. The second component interval is I2, closed interval 1 by n, 2 by n. In this way, we have the kth component interval ik is equal to k minus 1 upon n, comma k upon n. And so on. We define here the nth component interval in is equal to closed bounded interval n minus 1 upon n upon n. And we'll clearly see that the length of all these component intervals are the same, that is 1 by n. Then here the maximum for function f over these component intervals ik are defined as a least upper bound of the function f of x belongs to I. The function f of x is x, so the least upper bound in every component interval is k by n. Then this upper sum for f becomes, corresponding to the subdivision sigma n, becomes summation k is equal to 1 to n maximum for the function f corresponding to the component intervals ik into length of ik. Clearly here the maximum is k upon n, and therefore we are getting here summation k is equal to 1 to n k by n into 1 by n, that is the length of n. N is constant, so we will take it outside the summation sign, and we are obtaining here 1 upon n square into summation k is equal to 1 to n k. Clearly this means it is the sum of the first n integers, and by formula sum of the n integers is n into n plus 1 upon 2. So here this summation is n into n plus 1 upon 2. Simplify this, we will get n plus 1 upon 2n. So here the upper sum for f corresponding to subdivision sigma n is equal to 1 by 2 1 plus 1 upon n. So this can be rewritten as this one. Now we will take the limit of the upper sum. So here limit n tends to infinity of upper sum for f corresponding to subdivision sigma n is equal to limit n tends to infinity 1 by 2 in bracket 1 plus 1 upon n. Now take the limit. This 1 by 2 is constant, so we will take it is outside the limit, and we are getting here 1 by 2 into limit of 1 plus 1 upon n. Clearly the limit of 1 as n tends to infinity is 1, and limit of 1 by n is 0, and therefore we are getting here 1 by 2 into 1 plus 0, that is, after simplification we get 1 by 2. That is limit n tends to infinity upper sum for f corresponding to sigma n is 1 by 2. Yes. This is in the first part of the Riemann integral. In second part we will see the definition and corresponding theorems to that one. Thank you.